and the first speakers are Esraaj and Bhuvan. Start off.
So, good morning, I'm Esraaj, and we're going to be presenting on the study and synthesis of a 2D material called graphene. So, I'm sure we're all familiar with an instance like this. It's very clear that this is because we use glass in our touchscreen. And believe it or not, glass isn't exactly the ideal material for a touchscreen. So, the criteria for a touchscreen is to be transparent, which glass is, and to be conductive, which glass isn't. So to solve this issue, we coat glass with some metals, particularly rare metals like indium or some compounds of indium, to make it conductive. But again, it's glass, so it shatters very easily. And we do have a material that can solve this issue, and it's called graphene. So let's take a look at what graphene exactly is. So graphene is a 2D allotrope of carbon. And when we say 2D, we don't mean mathematically 2D. We don't mean that it has a thickness of 0. In material sciences, anything with a thickness of less than 100 nanometers can be classified as a 2D material. So you must all be familiar with the lattice structure for the structure of graphite, where you have these layers, these hexagonally bonded carbon atoms in layers on top of each other, bonded by van der Waals forces, giving us graphite crystals. So each one of these layers can be called a graphene layer. This one layer over here of hexagonally bonded carbon atoms can be called graphene. And so essentially, the reason we are interested about graphene is because it has quite a few extraordinary properties. For example, it has a tensile strength of 130 gigapascals. It's the strongest material we've tested so far. Apart from that, it has a Young's modulus of 1 terapascal. And on top of this, it has a high electrical conductivity of 18 megasiemens per meter and a high thermal conductivity of 5000 watts per meter Kelvin. So let's talk about the mechanical properties of graphene. So here you can see a stress strain graph for graphene, and you can see that it fails around 140-150 gigapascals. Compare that to the ultimate strength of steel, which is only 500 megapascals. And the reason graphene is so strong is because of its structure. Now you can see I've visualized the geometry right over here, and this structure of carbon is particularly stable. It very much dislikes any sort of in-planar deformities, and so it takes a lot of energy to change the bond length in this kind of a structure, making it exceptionally stable and exceptionally strong. When look at the conductivity of graphene, here is the band structure of graphene. I'm assuming everyone has a brief idea of what a band structure is, but I'm just going to go through it just one more time. So essentially, a band structure, you have your these lines represent your energy levels. We have the energy level graphed in the y-axis, and the x-axis, it represents real space. So now you can see over here, in every band structure, we have these things called valence bands, which visualize the ground state energy of our electrons, and this dotted line over here, which is our Fermi level. Above these, you normally have your conductance bands, and electrons in the conductance bands are essentially mobile electrons. They move freely, and it's what gives conductors their property of conductivity. So now in dielectrics, you normally have a significant gap between your conductance band and valence band, but in graphene, you can see over here, which is a very good conductor, there is essentially no gap between the conductance band and valence band. This allows electrons in the valence band to jump easily into the conductance band and become mobile electrons. Another reason graphene is conductive is because of its delocalized pi electrons. It does have outer plane pi bonds, and these electrons are also delocalized over the plane due to conjugation. And these electrons as well contribute to the electron mobility for electrons on graphene. And conductivity is directly proportionate to mobility. So you can see the conductivity of graphene is roughly 18 megasiemens per meter. Compare that to copper, which is just 60 megasiemens per meter.
Now that we've seen what graphene is, let's see how we synthesize graphene. The first ever method used for the synthesis of graphene is called mechanical exfoliation. It was first used by Andre Geim and Konstantin Novoselov in the year 2004, for which they received a Nobel Prize in the year 2010. So the procedure consists of three major steps. The first step is the cleaning of the substrate. For our samples, we used the silicon dioxide substrate. So to clean it, we first submerge it in ethanol and then 5 minutes of ultrasonicator. We repeat the same for isopropanol and DI water. This will remove the impurities in the substrate and will be ready for the exfoliated crystals to be planted. The second is the actual mechanical exfoliation of graphite itself. To do this, all we require is a scotch tape and some graphite. We first peel off a layer of graphite using the tape, and then we keep sticking it and peeling it. So it keeps reducing the number of layers of graphene. This works for graphite because the layers of graphene are held together only by weak van der Waals forces. The last step is the planting of these exfoliated crystals onto the substrate. We can simply do this by pasting the tape on the substrate so the crystals go onto the substrate. It usually takes a lot of tries, so we weren't able to get single layer graphene, but we were able to reach up to 3 layers.
So another way we can prepare graphene is through something called chemical exfoliation. So instead of using mechanical force to separate the layers, we use some energy provided by chemicals. So what we do is we take graphite powder and we dissolve it in we suspend it in some sort of solution like ethanol or acetone, and we need to do a few things with this so that we can make this into our graphene. So first thing we do is add some anti-agglomerants to our solution. Graphite in its solution, in its liquid phase, tends to clump together because of the van der Waals forces between them. So we add some sort of anti-agglomerant like acetone. Conversely, we could try some mechanical anti-agglomeration techniques such as stirring or heating, which should work in theory. And then what we need to do is we need to supply some sort of energy to break the bonds between our graphene crystals, graphene layers in our graphite crystal. So what we do is we add some sort of electrolyte such as lithium fluoride or sodium chloride, and the energy released from the dissociation of these ions should in theory be enough to break the bonds between these layers and give us single layer or multi-layer graphene crystals. And then all we have to do is clean the powder that is thus obtained, giving us some moderately good quality graphene powder. We were unable to do this ourselves because, well, lack of time and lack of reagents. It takes a lot of planning. But this should in theory work better than mechanical exfoliation.
Now that we've seen how we synthesize graphene, let's see how we detect and check the quality of graphene obtained. We use 3 major methods. The first one is Raman spectroscopy. To understand what Raman spectroscopy does, we need to understand what's Raman effect. So when you subject any atoms or molecules to photons, they absorb this energy and the electrons get excited to a virtual energy state. And upon getting de-excited, they usually come back to their initial vibrational state and release the photon of the same wavelength they absorbed. This is known as Rayleigh scattering, and it's very common. But roughly about 1 in a million of these electrons get de-excited to a lower or higher vibrational state, thus releasing a photon of different wavelength. This is known as Raman effect. So Raman spectroscopy works on this principle. The major components of Raman spectroscopy are an excitation source, the sample, optical filters and CCD detectors. So first when we shine the laser on the sample itself, a part of them, the part of the molecules we shine it on, the electrons get excited to the virtual state. So they can undergo different types of scattering. So when all this scattered light passes through the notch filter filters out the initial laser light. So only the Raman scattered light pass through. Then they undergo spectrograph grating, which basically means splitting them based on their wavelength. And then they fall on different positions on the CCD detector. Based on the position where they fall on the CCD detectors, we'll be able to find their wavelength, and after we analyze this through a computer, we get a Raman spectrum generated. We prefer Raman spectroscopy as it's non-contacting and non-destructive, so we can measure the same sample multiple times using Raman spectroscopy. This is the Raman spectrometer we use for our samples, and that is one of the graphs we obtained. The y-axis contains the Raman intensity and the x-axis is the wave number. So different molecules and bonds have different Raman intensities at different Raman shifts. The first one is the silicon peak. That is because we have silicon in our substrate. then the second one is called the graphite peak or the G peak, and the third is called the 2D or graphene peak. We say we've obtained a single layer graphene when the 2D peak is higher than the G peak. As you can see, we haven't got a single layer graphene, but it's only a few layers. Another method we used was the scanning electron microscopy. Scanning electron microscopy uses electrons instead of photons for imaging. It has a higher resolution than optical microscope. You can precisely measure objects that are over 50 nanometers. These are a few of the images we got using scanning electron microscopy. The first one is the substrate. The other three are graphite crystals or a few layers of graphene. As you can see, they have a few layers, and you can see a single layer up there in the last corner. That is the scanning electron microscope we used. So now let's see how a scanning electron microscope works. First, the electron source projects electrons when the thermal energy is higher than the work function. So these projected electrons are attracted and accelerated by the positively charged anode. To control the path of these electrons, we use something called as electromagnetic lenses rather than optical lenses, since electrons do not pass through glass. Electromagnetic lenses are basically coiled wires inside metal pipes. So when you induce current in these coils, they generate a magnetic field, and since electrons react to magnetic field, you can control the path of these electrons by altering the current you pass. So the first electromagnetic lens is called the condenser lens. This electron beam is passed through the condenser lens, and it's concentrated to a singular point. The condenser lens also helps you to determine the size of the electron beam. The second is the scanning coil. Scanning coil basically helps you raster the beam onto the sample. It's for scanning. The third is called the objective lens. The objective lens is the last electromagnetic lens there, and it basically helps you project the electron beam to the part of the sample you want to image. So when this electron beam interacts with the sample, it releases a lot of electrons and radiations. There are two major types of electrons that are released. The first one is the backscattered electrons. The backscattered electrons are the electrons from the initial electron beam itself that undergo elastic interactions and are scattered everywhere. These are detected by what we call backscatter electron detectors. And then the second type of electrons are the secondary electrons. The secondary electrons are the electrons from the sample. Since they undergo inelastic interactions with the electron beam, they are ejected with a lower energy. These are detected by the secondary electron detectors. And the last ones are X-rays. X-rays are detected by the X-ray detectors, and all these signals are used to produce an image on the computer screen. So the reason we use electrons is because photons have the constraint of wavelength, and since electrons have a very small wavelength, they give a higher resolution and higher magnification. Also, all this system has to be in a vacuum, since the electrons will be disturbed by other air molecules.
Yeah, so we just went through scanning electron microscopy, and this is not a primary method of imaging. One of the reasons we don't use scanning electron microscopy as much is because it takes a lot of energy. We need to induce a vacuum in the chamber, and it takes several kilovolts energy provided to the electron so that it goes and hits our sample. It's very energy consuming. So what we do instead is we use atomic force microscopy, which yields us an even better resolution mapping of our substrate. So what we do in atomic force microscopy is that we have a very small needle denoted by number 4 over here, mounted to a cantilever denoted by number 1. And what we do is we bring this needle, which by the way is the tip of which is on the order of couple nanometers. You can see an image of it right here. This is the tip of the needle, and here you can see the needle mounted to the cantilever. So what we do with this needle is we bring it very close to our sample. on the order of angstroms, and the reason we do this is because we want the van der Waals forces that are present in our graphite or graphene crystal to start interacting with the needle. Then what we do is we oscillate the cantilever and needle at a known frequency, a constant and known frequency, and then we essentially wait for the van der Waals forces to interact with this needle, which will then change either the amplitude or frequency of oscillation, which is then picked up by a laser and a photodiode denoted entirely by number 5. And so these changes are then measured and recorded, and that gives us an idea of what the topology looks like. So over here, this is what the scanning electron microscope looks like for us. It's much simpler than an SEM. It takes less energy to make this work. And these are the results it yields. So on the first diagram, you can see a graphite crystal. In this graph, you can see it ranges from around -20 nanometers to 40. So that will give it a thickness of around 60 nanometers. But this second crystal over here, you can see is roughly 6 nanometers thick, which is less than 10 nanometers. So this can be called a graphene crystal. It's not a single layer of graphene. It is multi-layered graphene, but graphene nonetheless. So here you can see our since we use mechanical exfoliation, our crystals are also very small. You can see that their width is on the order of a couple microns. So going back to my initial analogy, I started with phone screens, and the reason we can use graphene as very good in phone screens very efficiently is because one, it's transparent. Single layer graphene is transparent optically. Second, it's electrically conductive, so it negates the need for any sort of metals that need to be coated onto our glass, and so it's much stronger than glass, so it probably won't break as much as it does nowadays. Apart from that, we can also use it on a multitude of other applications. We can use it to coat military grade equipment. That will make it a little bit stronger and also a little bit lighter, since graphene is just single layer of atoms. And we can also use it for efficient heat sinks. Now, graphene is very small. It's a single layer of atoms, and it's a very good conductor of heat. So we could end up using it in the future for some sort of microelectronics for efficient heat sinks. So that will be all. Thank you so much for your attention. We will be taking questions now.
Comments, questions?
Okay. So in your Raman spectroscopic, you have different heats for graphite and graphene. Why is that? Shouldn't you get the same heat when they're both carbon?
Oh yeah. In graphite, the graphene layers are held together by van der Waals force. The van der Waals force also affects the graphene, the Raman peaks there. So you have a different one for graphite and graphene.
In the STEM microscopy, how do you differentiate from the backscattered electron and the electron that comes out?
Yeah.
And one more question: why does using electrons in they have a smaller wavelength, right? Why does that give us better magnification? And why is that better?
Okay, yeah. In optical microscopes, photons have it basically uses the concept of diffraction, limiting diffraction. So you can't see something which is 0.2 millimeters apart. You can see only up to that with your eyes, bare eyes, without lenses. So an optical microscope gives you a maximum magnification of like up to 1000 times. But then with SEM, with the use of electrons, you can push that to 2000, 3000 stuff.
And what was
Yeah, so the difference between backscattered electrons and secondary electrons is that since backscattered electrons undergo elastic interaction, they have the same energy that they are projected with, whereas the secondary electrons have a reduced energy since they undergo inelastic interaction.
How do you exactly know that the layer of graphene which you obtain is exactly similar? Is it any method of verification?
Yeah, so one way we can do that is just looking at our atomic force microscopy result. If this was a little bit thinner, for example, in the order of 2-3 nanometers, we could estimate it to be a single layer of graphene. But again, it's very difficult to produce such results with rudimentary methods like mechanical or chemical exfoliation.
Yeah, so you say that graphene is a viable it's a viable product for all these different kinds of applications. What is the progress when it comes to research or the manufacturing process of graphene on a large scale?
Yeah, exactly. So the manufacturing process of graphene is very difficult because to get all the properties I just mentioned, you need defect-free graphene. Even small defects in the graphene will drastically reduce your mechanical properties, especially, and also your electrical properties. So currently, the best we've gotten is, I think, 1 centimeter by 1 centimeter layers of graphene that are completely defect-free. You have bigger sheets of graphene that are produced industrially, but they aren't completely defect-free. So that's the gap. We need a better synthesis process, really.
So was that done using mechanical exfoliation or chemical?
So there are a couple more ways you can make graphene that I didn't discuss because of the constraint of time. But you can produce them electrochemically or pyrolytically. The two I mentioned are the most rudimentary, and I think we're out of time. So thank you so much for your attention.